everyone. Welcome to Tah Poe Seminar, Series 51 and talk number 6. And today our speaker is Dr. Salvatore Vincenzo. And today he will tell us about 1D point interaction in non-relativistic quantum mechanics. Please welcome our speaker.
Okay. Thank you very much for your kind words, Pongwit. The topic of my first seminars here at IF is one of the subjects I love the most. Probably is the second issue I love the most. I think I had a love with this topic, just like love at first sight, you know? But the first one was the Dirac relativistic equation, or the Dirac equation, the quantum relativistic, all that kind of things. But this topic is especially beautiful, and I love, again, a lot. I really love the topic. I hope you can love too the topic after this seminar. Okay. The problem here is as follows. Imagine just a real line with a point. In that point we can have, for example, a singular interaction, or a hole, or an obstacle, or a defect in the physical system. And we would like to describe how a particle can interact with these kind of things. In principle, it's very simple, but it's not so, really. You can read in the screen. We're just considering here non-relativistic point interactions, okay? Also, you can have relativistic point interactions. This is also a topic very interesting. And also in this seminar, I just want to try with Salvatore point interactions, just Salvatore. This is particularly important, but right now you can use also non-Salvatore operators. For example, PT operators or symmetry operators. This kind of operator can give us a spectrum or a spectra that is real also, just like the Salvatore point interactions. Okay, that's the first thing. What is a point interaction? This is the response of that, the answer of this question. An idealized, localized single interaction, zero range, zero. So the interaction, the single interaction is zero everywhere, but just in a point it's not zero, okay? Just in one point. Okay, this kind of thing or interaction can be described in two ways. Probably you know this because all of you guys know a lot about the delta. In fact, you can resolve or you can describe the problem of the point interaction, of a point interaction, just with boundary conditions, no singular potential, or just with singular potentials. Okay? Two ways to resolve problems. In principle, you will love to have just boundary condition because the potentials involved here are very singular. They are combinations of Dirac deltas. You will see that thing. Okay, a point interaction is the same of contact interaction, zero range interaction, delta interaction. In the literature, you find all these words. Obviously, point interactions, singular potentials, can be considered as good approximations of highly localized real interactions between two bodies. Okay. Okay, the problem is, looks like, oh, very simple, but we have in the, not just recent years, since last more than 100 years, we're treating with this kind of problems. Almost 100 years, in fact. Okay, in this seminar, just this case. The real line, just one single interaction at x equals 0 at the origin. Okay, it's very simple, but it has a very rich structure. I will convince you about this. Okay, the history of the topic. Okay, all you know about the Kronig-Campani model. The Kronig-Campani model was the first model of using point interactions. In 1935, we also have here two papers by Thomas or Beer and Peirce, okay? They use point interaction to resolve problems about scattering, theoretical, in fact, neutron-proton scattering. Also Fermi treated with this problem in 1936. And he introduced the so-called delta pseudopotentials. All we know about this kind of potentials. But it's just a delta with a derivative. So it's very common in nuclear physics. But the first rigorous analysis of this, of a point interaction in 3D, was made by Beresin and Fadeyev. This is a beautiful paper. It's a beautiful paper. The first serious intent to understand the math behind the topic, behind a point interaction. Okay, as follow, this looks like a bunch of papers. No, it's more than that. These are the papers and the literature about the topic, especially from Bavaria. We have here mathematicians are also theoretical physicists. These guys, mathematicians, Kurasov mathematician also. A physicist. Ah, also Caro, yes, very important. Okay, a lot of results were obtained from these guys, but the topic has remained very active. And if you Googled the phrase point interactions, you will see a lot of paper. Every day we can obtain 2 or 3 or 4 papers about the topic. Okay, I will explain a little bit more about this at the final part of the seminar. Okay, so we have point interactions. Okay, they can be boundary conditions or they can be singular potentials, or one thing or another thing. For example, this is the most simple Hamiltonian we can have. We have here the real line, but not the zero, without the origin. This operator must be Slavgen. You know why? Okay, the spectra, both here, if we have, must be real. You can demonstrate that just with this boundary condition, this operator is a Slavgen. For example, use this theory. The Neumann's theory of Slavgen extension is just a method to obtain the conditions, the appropriate conditions to obtain an extension, Slavgen extension from a symmetric operator. Symmetric, okay, Hermitian operator, okay? Okay, with these definitions, lambda is a parameter, and this matrix must be unitary. It has 4 real parameters. It's beautiful to do this calculation and demonstrate this. This is the most general boundary condition a Schrodinger wave function can support at x equals 0. The most general. We have a lot of boundary conditions here. In fact, we have an infinite number of boundary conditions. Okay, with these restrictions are imposed by the fact U is a unitary matrix. Okay. This is not just a math topic. This is very important, also for us physicists. We need to be sure the operator we are treating must be self-adjoint or PT symmetric, for example, because this last kind of operator can also give us a real spectra, as Bender, an American physicist, proved 20 years ago. Okay, have a look at the boundary condition. Very general, right? It's very general. In the real line, without the 0. Okay, the particle can be here, on the left side, on the right side. Could be here, be here, could be here, could be here. So it's just like a particle inside a box. The particle can be here, but neither here nor here. You got it? It's the same. So these 2 problems, a particle in a real line just with a defect in a point, shows similar characteristics with the particle inside a box. Okay, because of that. Okay? This is very important because you can obtain a lot of result in this system, but also in the particle, the famous problem, particle in a box. By the way, this particle in a box problem is just a problem. I had worked a lot with this problem, and I always obtain a new result. It's very interesting because it's simple, but in one dimension it's very rich in structure. Have a look. 4 parameters, an infinite number of boundary conditions. The Dirichlet boundary condition is just one of the boundary conditions right here. Okay. Okay, this general boundary condition can be written different ways. This way is one particular interesting and important. Okay. Probably you are thinking about, okay, you have a lot of boundary conditions, so you have different kind of worlds at the origin. Yes, that's correct, sir. That's correct. Probably also all you know, okay, but this is the Dirichlet interaction. Oh, it's very easy because the wave function is continuous at the origin, but it presents a discontinuity, the first derivative, you know. Probably in your courses, quantum mechanics, you have teach this topic, but just this topic. Have a look at others of this point interaction. Obviously, this is a kind of point interaction. In fact, it's just I can demonstrate this. This is a 1 parameter, so it's really this related to the strength of the delta. Okay, I will prove this. Okay, this is the so-called the first derivative. Okay, it's not important the names right now because the names can be understood the final part of the seminar. Okay, okay, this is just a name. Okay, have a look at this. You remember a little bit to the periodic boundary condition, right? But it's not. Also, we have here another boundary condition different to this. Oh, we have a very common boundary condition here, the famous diversion boundary condition. And this is also very famous, the Neumann boundary condition, just the first derivative in a point. Probably in the waves courses, when you explain the string attached at the wall, you use this in one of the end surfaces or the ends of the box. Yes, yes. And this is the part, according to me, more beautiful. Okay. Do you see a potential here? No. You don't see a potential here. But who is this guy? A very singular potential. This is a very plausible expression for this potential. Symmetric. Delta, delta, delta prime, delta, delta, delta prime, delta prime, delta prime. A, B, C, D are complex constants. Okay. Okay, this object here is a scalar product, right? But if you know a little bit of distribution theory, you know this is just this quantity here, 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 and here is the same of the action of the distribution on a test function. Okay, okay, look at the expression. This potential is waiting for a wave function. When you put here on the right hand side a function, the function must be here, 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 and here. But you need to define this. Okay, this is very easy. The more common property of the delta. This is not so common, but it's very easy too. The action in this function, okay, delta and delta prime are distributions, in fact. And that's it. Okay. If you want to relate this potential with the most general boundary condition here or here, you need to satisfy Kent is not a proper operator. So this operator is not a proper operator on the square. Okay. It's not a proper operator, but if you can relate this with another cell adjoint, probably you need to use these boundary conditions. Yes. The problem here is, okay, I use this, construct the domain of the operator, and I put this boundary condition. Okay, a problem. Another problem because it's not cell adjoint. But it can be extended. In quantum mechanics, you have a lot of times these kind of things. You have a very strict operator, the closure. Very strict operator. And from this operator, you can see, oh, must be extended. Probably yes, but at times you can't. In this case, you can. Okay, the domain is practically this space. It's practically. And you can demonstrate that this operator in this space is a subtle of space. It's technical, okay? You can ask me about this after the seminar if you want. But the extension of the operator with this condition gives us this boundary condition. It's beautiful because they are the conditions you teach to your students. In fact, this continuous and discontinuous at the origin. Also, it's important to note that if B is this is a zero range. So this is practically zero. It's this part is practically zero. But it's not zero at the origin, obviously. Okay. Finally, you obtain in a math way, no, but properly way, that this operator is just the extension of the first operator. This. Also, it's a natural definition of, in the framework of the theory of Salatian operators. Very good. Oh, still clarifying. It's not difficult. I'm using here another part of the operator, of the potential, no? This part is G4. G4, okay. G4 is here. Who is this guy? You can use a similar procedure and you can demonstrate, first, this operator is not a proper operator. It's not. Because the action of the operator on AC belonging to L squared is not a part of L squared. So you use this condition to try to obtain an extension of the operator. You can find this extension and you obtain finally this operator, because this is 0 everywhere, almost everywhere, with these boundary conditions. Oh, okay, so it's just like similar to the boundary conditions in the Dirac delta. You can compare. In the Dirac delta, you have continuity of the wave function at the origin, discontinuity at the first derivative. In the other, you have continuity of the first derivative, but a discontinuity on the function. This aspect is interesting and very useful. Okay. Remember this. This part, the action, the value of the distribution. Okay. What is? Okay, this part is this, because you see this in the screen. But can I write this ansatz? Can I choose this ansatz here? Is this plausible? Okay, plausible is. Okay, the problem is not always this is true. Okay, if the action of the delta on a continuous function at the origin is this, but it's also this, right? It's also the same. Also for the first derivative of the delta, okay? But if the function is not continuous at x equals 0, this is not true always. It's a fact. It's a fact. You can demonstrate in some cases. Also, I have demonstrated, also in the last year, I published a result about this in the Klein-Four-Gordon theory. I obtained a result when this is equal to this, but it's not equal to this. Okay? So, the reason is that there are situations in which that choices don't hold. For example, if C is defined by a differential equation, it's a case. Okay. There is a plausible choice here, because we on the choice can connect using the theory of Salatian operators, singular potentials with boundary conditions. Okay, let me connect in this. We have 30 minutes, right? 30 minutes? I can go faster. 30 minutes? Okay. My God. Are you sure? Won't wait. Okay. Okay, let me connect in this fast. Okay? You have the Schrödinger equation, and you have the potential here. You can integrate the Schrödinger equation this way. Okay. From here, around the origin, and take this limit. And then you can integrate again, but in this interval, and then one more time here. Okay, you obtain this. this pair of equations or relations take this form. Oh, just like a boundary condition. Compare this with this. This with this. The same. This is the connection. So with this, every formal, okay, I use the word heuristic because it's heuristic formally. It's a logical operator H with a singular potential. Okay. In other words, any local potential, depending on Dirac deltas and derivatives, can be associated with a boundary condition and vice versa. This is a result very interesting. Okay, some examples simples, but some of them are not so simple. This is Dirac delta. You know, okay, these are the relation between the parameters. And you can demonstrate we have here bound state, one single bound state, yes. The point interactions have a condition or a characteristic very interesting. They have 1 or 2 or 0 bound states. So scattering state is more, we have a lot here, yes, because this kind of interaction is very appropriated to simulate interactions scattering type, okay? But it's also interesting to comment about this. This is obvious. You have here the delta, and this is the bound state. Just one bound state. This is a well, deep well. Is deep well right? Is really a deep well here? In fact, no, because this point, this wall is penetrable. It's not an impenetrable barrier. It's interesting. Okay, the first derivative. This operator, this part, is just this part. And you can show we don't have here a bound state, just a trivial bound state. Okay, no problem. Also, the point x equals 0 is a penetrable barrier. Okay, in the math term, you say the discrete spectrum is empty, you know. This where point interaction, have a look at that, at this. And here we have something very interesting. Probably you use a lot of boundary conditions in your research. For example, periodic, for example, antiperiodic, for example, Neumann, for example, Dirichlet, for example, Robin, boundary condition, or others. But you can demonstrate this beautiful result. If you use the antiperiodic boundary conditions, this is equivalent to this potential. So in your studies, you can replace this boundary condition for this potential. It's the same. A boundary condition, a singular potential. Beautiful. If you have the periodic boundary condition, you have the potential 0 or constant. Is what we were expecting, obviously. But it's a result very interesting, in fact. Other interesting result is this. Just formal manipulation, you can demonstrate. We have here P, the vector potential, a kind of, and also a potential, electric potential. This is exactly the part with this potential. So if you have a gauge or a choice you have with A, with the vector potential being a delta, probably it rates with this potential, because you can write this in this way. Also, you have here a discrete spectrum, empty. This is more common, probably it's beautiful boundary conditions. It's just similar to the Dirac delta boundary condition. It's just this potential. Obviously, we have here math conditions, but odd parity. Odd parity. Okay. You know what? You can relate the differential boundary condition with a potential. Also with a potential. With a potential, yes. This is the strength of the direct delta interaction. If this strength is minus infinite, you obtain this potential, the square of the delta. The square of the delta is the differential boundary condition. So the delta at the origin is not an impenetrable barrier. But when you have delta square, yes, it is an impenetrable barrier there. Okay, the bound state could be calculated from the example A, obviously, because we have the result from this potential, and it's just a limit. If you have there, you obtain something interesting. The bound state is the square root of the delta. The square root of the delta, yes. Formally, okay? But after this, you must do an analysis using the distribution theory, and you can demonstrate we have here also a trivial bound state. That's it. And now the origin is an imperceptible barrier. That's what we all know about the differential boundary condition. Also, the normal boundary condition leads us to this result, and we obtain the Neumann boundary condition. It obviously is an impenetrable barrier. Okay. Other little result about this is you can separate boundary conditions impenetrables and boundary conditions penetrables. Okay? All these boundary conditions satisfy this. Okay, the density current is continuous at the origin. But for some of them, you have this, because you can demonstrate this relation. This is the density current. When you have this, it's zero. So the origin is an impenetrable barrier. Otherwise, it's penetrable. So you can separate these boundary conditions in just two cases. We have situations in which this is not true. It's a fact. For example, in the direct equation in one dimensions, you have a problem here because you can demonstrate the proper boundary condition using for this potential. It's just this. But in the books, you don't see this boundary condition. You see this. It's incorrect. I can demonstrate. And this is because you have an equation here, so this is not equal to the right side, okay? It's not equal. It's not always equal, in fact. Another example, I have a lot of examples about this topic, about the problem when you don't have a plausible choice in the origin. This was demonstrated for me in a paper in the Clay-4-Gordon theory last year. I don't know if you know, but the probability density or charge probability, okay, in this theory depend on phi, the potential. in any step potential, this function is discontinuous. So this guy is discontinuous too. In that case, the mean value of this operator in the step potential, simple, potential very simple, is just quantum mechanics 1. But you can't obtain this quantity because the delta is multiplied by rho, but rho is discontinuous. So what about the right hand side here? Oh, which is the value of this quantity here? Okay, you can demonstrate integrating the equation, some result, and finally you obtain this is the proper result. This minus here, not plus. This is the correct. So this is another case when you can use a plausible choice at the origin, thinking about a continuity of the function at the origin. No, it's not so simple, the things. And finally, some concluding remarks, the best part. Any point interactions characterized by a BC, so a boundary condition, can be characterized also with a single interaction. The Dirichlet, the Neumann, and the perturbation. They all have a singular potential. The most general family we have treated here, or I have shown here, is also the whole family. You can demonstrate we don't find another boundary condition outside. No. We have all the boundary conditions. All. This case can be treated. I have seen a lot of paper when you have a point interaction here, and here, a finite number of point interaction in a real line, an infinite number of point interaction. It's interesting. We have here a lot of result, beautiful result. Also, it's not the only way you can construct point interaction. You can use also renormalizing deltas. It's beautiful also the way. In this case, you can use if you are interested in the topic. And finally, nature seems to prefer selection operators. This is a fact. But I have seen people working in non-selection point interactions. They are also interesting, especially when they are PT symmetric point interactions. But you know what? Just 1 month ago, people are beginning studying non-selection relativistic point interaction. It's a very new topic right now, 2022. And finally, thank you very much to come to this seminar. Okay, I hope you have had fun with this seminar. Grazie mille per arrivare qua e anzi grazie per stare qua. Thanks. That's it. Thank you.
Okay, thank you very much for a very thorough presentation of this topic. So, does anyone have questions about this topic? Please feel free to ask our speaker.
Okay, questions. Okay.
Well, my question is that formally your first page, I think. No, another one. No. Yes, this one.
This one.
I just
this
wonder that how could you come up with that kind of domain of your
How?
How?
Thanks for the question. It's beautiful. Okay. You have almost three ways to obtain this. One of them is just algebraic. Okay? But the other way important is using this theory. You must try in the algebraic way, but in this theory, you can construct solution for an operator similar to this, but with complex eigenvalues, okay? You resolve there, and you must satisfy a condition, okay? If the condition is verified, you can say, okay, these are but the method contains everything about the result, okay? Okay, just, you must do the job, okay? But it's not so easy when you use this, but it's direct. If you want to know more about this secret ring, I can help you when you want. I will love, because for 20 years ago, I have been working in this kind of things. I would love to explain the methods. It's just a method with, you construct, okay, solutions for this operator, but with complex eigenvalues. And if a condition is satisfied, okay, you can say, we don't have extension. You have probably an extension, or you have extensions, and these bots resolve the problem. And finally, you obtain this. Okay, probably you are thinking about how obtain just these boundary conditions. Okay, you can obtain subfamilies. More easy, in a more easy word, okay? Wait. This is the most complete boundary condition, because we have the whole boundary condition in the origin in this theory. But in the literature, I have seen papers when the people, okay, they don't obtain the most general boundary condition, but they can obtain a subfamily with just 2 parameters or just 3 parameters, also just 1 parameter, yes. It's more easy, yes. But this is all, yes. In my doctoral thesis, I trade with this kind of problem, because I remember the singularity here is just like a particle in a box. It's just like, okay, it's not, they are similar problems, but obviously they also have difference. Okay, but you can treat them in a similar way. Sorry if my response is not enough for you, but probably no, because it's technical. Yeah. I would like, give me a piece of chalk. I would like.
Can I go to another one?
Yes.
Okay. So on the same page, actually, the U here, the U operator there.
Here?
No. The same page. Yeah. It's the U there. I mean, the U operator there. It looks to me like the one that we have in group theory, right? It's more like the same. Like
No.
It's not the same, right?
No. But okay, when you have this,
this is the map, right? This U is a map, right?
Yes. We have 4 parameters. Yes. So this matrix belongs to U2. U2, the group.
Yeah,
U2.
Definitely, yeah.
There, you can connect the parameters of certain groups with the result of the Neumann's theory. Yes, it's not exactly the same, but you can connect. Yes, in this case, the result important is, okay, must be a part of U2, not SU2. No, it's U2.
Yeah.
Because we have 4 real parameters.
Yeah, because actually that equation gives you the hyperspherical, right? The parameter M there.
M.
With the unit.
We have 3 independent parameter plus phi, 4.
Yeah.
3 plus 1. Yes.
Yeah. It's
yes,
a
3 plus 1.
sphere in 4 dimensions, right? Yeah.
Yes.
Okay. All right. Okay. And so, can I go to another one? Yeah.
Absolutely, yes.
So it seemed to, later it seemed to me that if you should, it seemed to me like if you impose different boundary condition, you will get different potential, right?
Yes.
Is that one? And
okay, do you want to know if 1-to-1? Yes. Okay, no. Okay.
So what it means is that is somehow the behavior, the system depends solely on the way that you impose the boundary condition, right? Is that right?
Yes. One boundary condition, a potential, okay?
Yeah.
And vice versa.
All right. Okay.
Yes.
Okay. Yes.
Right now, I'm thinking about some cases when you can have one or two of both similars. No, but we don't have here that kind. No. Yes. Boundary condition, you have a potential. Yes. Yes. Probably you in your theories, if you can resolve problems in other theories, you can use potentials instead of boundary conditions.
All right. Yeah. That's all.
Okay. This is just the real line.
Yes.
4 parameters, real parameters.
Yes.
An infinite number of boundary conditions. When you go to R3, the 3 dimensions, you obtain a lower number of boundary conditions. So the world in 1 plus 1 dimensions, or in 1 dimension, is more complex than the world where I live in. It's not a contradiction. For example, when you have the problem, simple problem, an electron around the proton, you just obtain 1 boundary condition, the regularity boundary condition. Do you remember the regularity boundary condition in quantum mechanics? That's the extension of Friedrich. Just 1 boundary condition and you obtain the spectra. You can change the boundary condition, okay, you obtain some different value of A. But these values have not been seen never. So the condition in physics, self-adjoint is the condition. Bender, an American physicist, 20 years ago, something like that, obtained a beautiful result. Okay, he knows PT symmetric operator can give us a spectra, real spectra. Very interesting indeed. Yes, it's a fact. But we don't see so much systems in nature with PT symmetric giving us these real spectra.
What I understand is that people in this field, I mean PT symmetric, they try to connect to the Riemann problem somehow. And then they go on. And they have been active, I think, for like 10 years so far, maybe more than 10 years.
See, more.
Yeah.
Yes, PT symmetric, yes. Okay. Do you have any questions? I would love to respond to questions about this topic because I love the topic.
Okay. Does anyone have further question to ask?
I'm not sure. Okay. So, what I get your idea is something like any kinds of boundary condition will link to a kind of singular potential.
Yes, that's the conclusion, yes.
Yes, and you just mentioned that if a singular potential here in the origin point, and it can be treated like a potential wall, right?
Yes.
In quantum mechanics, we know, for example, the infinite potential wall, they have infinite number of bound state solution. But for the delta function, we just have 1 bound state. So are there any link with this kind of?
Yes. A particle in a box is related with a particle in a singular point interaction, yes. But point interactions are more appropriated to describe scattering states. The other problem just give us bound states.
Yes.
It's different. Infinite number of 1 bound state, yes. I can connect conditions in here, just at the origin, with conditions in a box.
Yeah, so are there any relation between these solutions? I mean, the real physics problem solution and the singular potential solution, are there any relation? Because what I confused is about in real system we got multiple number from the state. It is in infinite potential world, it has infinite number of potential world. But if we transform this problem to a delta potential, singular potential, it becomes no matter how you do it, at most it's just one bound state.
Yes.
So are there any relation between these kind of solutions?
It's a fact in point interactions, in theory of point interaction, non-relativistic or just relativistic point interactions, you have a few number of bound states, very few, but it probably must, I'm trying to say, must be related with properties of the Dirac delta. Yes, because when you have representation of the Dirac delta, you conserve the area under the curve, because the integral of the delta must be 1. So it's not a square well, just a square well. It's a square well, but with that condition. And that's the point. When you have a square well, for example, finite well, you have a finite number of bound states, but no restriction about the area. But when you have distribution, just like the Dirac delta, you have that distribution. So probably that's the reason. In fact, this is the reason. You can demonstrate this. Just conserving the area in a value, you have just a little number of bound states. But in the other case, no. Actually, when the deep is 0, you don't obtain bound states.
Yes, but
About the well, square well, for example.
but suppose if the potential of any kind of boundary condition can transform to the singular potential. This is the idea of this theory. So I feel like if they are the same thing, so the solution must have some fitting or negative.
They are similar, but they have important difference too. When you say, okay, you have a particle outside the point, or you have a particle inside 2 walls,
Yes.
you can connect the families of boundary conditions. That's it. Okay, but they are different problems.
Okay.
In fact, they are different problems. I have seen things in one problem, point interaction, for example, and not in the other kind of problem. For example, in intervals, particle restricted to be there. An interesting point is this: you have a delta. Okay, a delta, for example, repulsive delta is a well. It's a deep well, but not so deep, because the origin is not an impenetrable barrier. It's not an impenetrable barrier. In quantum mechanics 1, you say to tell your students, okay, if the deep is very deep, impenetrability. No. The delta is a case. Okay, you have a delta, but it's singular at the origin, but it's penetrable. Just when the strength is singular, is infinite, you obtain an impenetrable barrier. So when you use distribution, you have these behaviors, not so common behaviors, but very interesting behaviors. Yes. If you want to talk to me about this or chat with me, I would love. Home. It's a topic I really love to treat.
So anyone else would like to ask speakers? If not, I would like to say thank you for a very interesting topic of today's seminar, and please thank you our speaker for the today's seminar. Thank you.
Oh, thank you very much.
And before we leaving, please take please take some time to respond our questionnaires about the today's seminar. The questionnaire are on the online link on the comment on the either on YouTube or on Facebook. Thank you for participating.
Can we have question on the internet? No, not right now, no?